Alright, hello everyone and welcome to our next video in AP Chemistry Unit 7, which is on equilibrium. Today we are going through lessons 7.5 and 7.6, and we are also going to have a little time to go through some of the most missed AP classroom questions from lessons 7.1 to 7.4. So that will be at the end of this video. So first we're starting with 7.5, which is the magnitude of the equilibrium constant. That is going to tell us how far a reaction proceeds before reaching equilibrium. So when K is very large, the reaction is going to strongly favor the products. When the K is really small, the reaction is going to strongly favor the reactants. So like discussed in our previous video, I like to think of my equilibrium constant as a point on a number line, and that number line to me is kind of represented as the balanced chemical equation. So if I were to have my balanced chemical equation and I have my equilibrium sign, I have my reactants and I have my products. So at the middle, or K equals 1, I am right in the middle of my amount of reactants and amount of products. So if I'm looking at a particulate diagram of the reaction at equilibrium and my constant is 1, I know I'm going to have the same number of reactant particles as I do product particles. Now, same as in my balanced chemical equation, if I move towards the right, I am moving towards the product side. So as I have a larger value than 1, at that particle level at equilibrium, I'm going to have more products than I would reactants. And same goes for the other direction. If I go less than 1, that means at the particle level, if I take a little snapshot of the particles at equilibrium, I'm going to have more reactants than I do products. All right, so let's break down this equilibrium constant. If I have an equilibrium constant that is very large, meaning 10 to the 5th or greater, it's what we call K is greater than 1. And what we mean by that is pretty much the reaction has gone into completion, which means that all of our reactants have pretty much turned into products. Now, if you have two K values, one being, let's say, 3.8 times 10 to the 7th, and one is 4.2 times 10 to the 30th. Clearly, our 4.2 times 10 to the 30th is going to have way less reactants at the particle level than our times 10 to the 7th. However, both of these are in that category of pretty much being all products if we're looking at the particle level at equilibrium. Then just saying K is greater than 1 would be an equilibrium like 6.6 times 10 to the 2nd, or 66, or 6.6 times 10 to the 4th. Now, all three of these K values will give you more products than reactants. It's just important to know that you will have reactants in your particle level diagram at equilibrium. And then same goes in the opposite direction. So if we have K is less than 1, so that could be something like 6.6 times 10 to the negative 2nd, or 6.6 times 10 to the negative 4th. These numbers are same as going in the opposite direction. At equilibrium, we have reactant particles and product particles. We just have slightly more reactant particles than product particles. And then K is less than 1, which means we might have a number like 3.8 times 10 to the negative 7th, or 3.8 times 10 to the negative 30th. When we're talking about K is less than 1, this is telling us that our reaction at equilibrium pretty much is all reactants. Now, we might have some products in the mixture. However, we're going to have majority reactants. All right, this example problem says at night an equilibrium reaction between two different nitrogen compounds generates N2O5 in the atmosphere. A mixture of NO3 and a 10-fold excess of NO2 are placed inside a rigid container at constant temperature and allowed to reach equilibrium. Which of the following provides a correct comparison of the equilibrium concentrations of these chemical species and why? So we can see in this example, we're given an equilibrium reaction where NO3 reacts with NO2 to form our product, which is N2O5. And we're also given our equilibrium constant. And we can see we have times 10 to the negative 11th, which means we have an extremely small K value, or something we would call K is less than 1. And what that means is that equilibrium, this is going to be heavily reactant favored or lie to the left. So with that information, we know that our concentration of our reactants is going to be much greater than the concentration of our products. And I want you to notice in my explanation to the answer of this question, I put the concentration of NO3 specifically is greater than the concentration of N2O5. That's because NO3 was our limiting reactant here. So in the question, it said that there was a 10-fold excess of NO2. So putting that the concentration of NO2 would be greater than N2O5 doesn't really have to do with the equilibrium. It has to do that they put a ton of excess NO2 in there. So specifically, we would be referring to NO3 since this was a multiple choice question. All right, and then here we have a reaction where zinc metal reacts with copper 2 ions to produce zinc ions and solid copper. And we have a very large equilibrium constant with times 10 to the 37th. And a K value that large should very quickly indicate to you that the reaction is going to strongly favor the products, and it's essentially going to proceed to completion. The question says a 0.1 mole sample of solid zinc is added to 500 milliliters of 1 molar copper 2 nitrate. After the mixture sits overnight, which of the following best describes what will most likely be observed and measured the next morning? So from our equilibrium constant, we can see that we have a very large K value, which means we're going to have a lot of products being formed. So the next night, you should be looking for an answer choice that talks about pretty much only products being there when they observe it. So looking at answer A, it says almost all of the zinc will still be in the beaker. So zinc is a reactant. So since we know we have such a large K value and will be on the product side of the reaction, this would be an incorrect answer because almost all the zinc will be consumed, not still in the beaker. Then B says about half of the zinc will have disappeared and Cu will have appeared in the beaker. So if we had a K value around 1, then this could be the answer. But because our K value is so large, we know all of our zinc will pretty much be gone. So that is wrong. Then we go to option C. It says about 2/3 of the zinc will have disappeared. Same explanation as B. And then we go to D. Virtually all of the zinc will have disappeared and copper will have appeared in the beaker because the reaction proceeds almost to completion at equilibrium due to the very large K value. And D would be our correct answer here. All right, moving on to 7.6, which is on properties of equilibrium constant. We are going to talk about how K behaves when we manipulate different reactions, just like we did in Hess's law for enthalpy. All right, so if you were to recall back to when we did Hess's law for enthalpy change in Unit 5, we went through the individual steps on how to manipulate delta H if you had to change the reaction that had that delta H value. So for example, if we were trying to get our overall reactions delta H value using a series of different reactions, if I had to flip the reaction around, then I flip the sign of delta H. If I had to multiply the reaction by 2, I would multiply delta H by 2. And if I, at the end, had multiple reactions that I needed to put together, I added up all of those delta H values. Now, the properties of equilibrium constant for Hess's law works kind of the same, but the manipulations are different because it's a reversible reaction. So if I were to reverse the reaction, and so now my products are reactants and my reactants are products, I am going to inverse the value of K, which should make sense, right? Because K is the relationship between the products over the reactants. So if I turn the reaction to go a different direction, that means I need to flip the numerator and the denominator in my K value. So if I were to reverse the reaction for Hess's law for equilibrium constant, I am taking the inverse of K. So it would be 1 over K. Next, if you need to multiply a reaction by a certain value in order to cancel out species, you are going to raise the equilibrium constant to the power that was multiplied. So let's say you had to multiply an entire equation coefficient by 2, then you're going to raise the equilibrium constant to the second power. And then finally, using our equilibrium constants for Hess's law, at the end when you need to combine all of the reactions, instead of adding all of your values, you're going to multiply the values by each other. All right, so as discussed in our last slide, if we need to flip an equation, we are going to take the inverse of K. So for the chemical equilibrium, we have A plus 2B reacts to form 2C, and we are given a K value of 10. Well, we want to find the K value of the same equation, but it is in reverse. So since it's in reverse, our new K value is going to be equal to the inverse of our original K value, which will be 0.10. So the answer is A. All right, so for this question, we're given the same starting equation with the same K value, but we are given a new equilibrium that we are trying to solve for. So we can see that A and B are reactants for both and C is a product for both, so we don't have to flip or reverse the reaction. However, we do need to multiply this entire reaction by 2 to get it to the same as our desired reaction. So remember, with Hess's law for equilibrium constant, when you multiply an equation by 2, you are actually raising your K to the second power, not multiplying it by 2. So since K is equal to 10 squared, our new K value is going to be 100. All right, so now let's do a Hess's law equation with 2 reactions with equilibrium constant. So same process as when we did it in Unit 5 with enthalpy. Now we are just manipulating the K's differently. So first, starting off with N2. N2 is in reaction 1, and I can see I have a half mole of it. So I need to multiply this entire reaction by 2 so I can get 1 mole of N2. And when I multiply a reaction by 2, make sure you are taking your K value and raising it to the second power. Then moving on to O2, I can see O2 is in both reactions, so I'm actually going to skip that just for efficiency and clarity and go to our product, which is 2NO2. That is only in one reaction, which is the bottom one. So I actually don't need to manipulate K at all. So just verifying that I did cancel everything out, I'm going to rearrange the reaction that I had to multiply so that we can easily cancel out units or substances. So N2 plus O2 reacts to form 2NO. So as you can see, our 2NO is gone. Our O2 combines, so we have one here and one here to form 2O2, which is what we want. And then we have 2 NO2s left. So this is our final equation, Now we just need to put these K values together. Now remember, for enthalpy, we are adding the values. For equilibrium constants, we are multiplying the values. So when I square 6.55 times 10 to the negative 13th, I get 4.29 times 10 to the negative 25th. And now I need to multiply that value by 6.9 times 10 to the 5th. And my final K value is going to be 2.96 times 10 to the negative 19th. And that will be my final answer. All right, and then one more example. Here I have my same example that we were working on before, but I have a two-step process to get my final reaction. So first we can see our reactants are on the wrong side and our products are on the wrong side. So I do need to flip around this equation and reverse it, which means I'm going to take the inverse of K. So the inverse of K is going to be 1 over 10, which is equal to 0.1. And then finally, I have to multiply this entire thing by 2 because I have 4 C's, 2 A's, and 4 B's as my final equation. So now we're going to take 0.1 and we're going to raise it to the second power. And that is going to give us 0.01 for our new K value. All right, so the next thing I want to do is go over the 3 most missed questions on our 2 AP classroom assignments that we had so far in Unit 7. So our first assignment was 7.1 to 7.2. The first question that I wanted to go over said that when AgCl is placed in water, it dissolves according to the chemical equation above. The particle diagram above was proposed to represent an aqueous solution in which AgCl is in equilibrium with its ions. Which of the following best explains whether or not the diagram provides a good representation of this dynamic equilibrium at the microscopic level? So first, we need to remember what dynamic equilibrium actually means. And at equilibrium, the system itself did not stop reacting. The key idea is that the rate that we are making products is equal to the rate that we are making reactants. Now, looking at this diagram, it is not a good representation of dynamic equilibrium because if we're talking about dynamic equilibrium, it means that the solid is continuously dissolving while the ions are simultaneously recombining to form the solid. And we see no evidence of that in this image. And we also see just a snippet of the particles at one period of time. So it doesn't actually show a change of anything. So the best answer for this one would be D, where it says it is not a good representation because it does not illustrate the dynamic equilibrium in which the rates of the forward and reverse reactions are equal. This next question says the particle diagrams above show the changes that occur after an equimolar mixture of X and Y were placed in a rigid container at constant temperature. Which of the following statements is best supported by the particle diagrams? So looking at our balanced equation, we have X plus Y reacts to form XY. So if we first start with our particle diagram at 0 seconds, you can see we have no product in the diagram. Now when we add 100 seconds, you can see we form 1 product molecule. Another 100 seconds, we now have 3 product molecules. And another 100 seconds, we have 5 product molecules. So from time 0 to 300, we are increasing our number of products, which is going to be the forward reaction. So the forward reaction is going to be a faster rate than the reverse reaction. So starting with option A, it says the rate of the reverse reaction is 0 because the concentration of XY keeps increasing. So when we have a reversible reaction, we have to have a rate of the forward and a rate of the reverse. If one of those is 0, then it's no longer a reversible reaction. So that would not be an answer choice. Then B says the reverse reaction is a higher rate, which we just proved was wrong. The forward reaction is a higher rate, so B is incorrect. C says the forward reaction has a faster rate, which is true, than the reverse reaction between 0 seconds and 300 seconds because more products were being formed. That is a correct statement. Now let's just verify D is incorrect. The rates of the forward and reverse reactions were the same after 100 seconds because the rate of formation of XY was constant, and it was not the same because we could tell between 100 and 200 seconds we were still converting reactants into products, which is the forward reaction, and from 200 seconds to 300 seconds, again, we're still converting reactants into products, so it's still a forward reaction. All right, and this was our most missed question on the 7.1 to 7.2 AP Classroom assignment. It says at a certain time, the partial pressure of the gases in the reaction mixture had values shown in the table below. Based on the information above, which of the following occurred as the reaction mixture moved toward equilibrium? So we know our equilibrium value is 66, which is product favored. So what we can do is take those partial pressures of our substances and plug them into Q, which is our reaction quotient. And that's going to tell us which way the current values are going to shift in order to reach equilibrium. And that will help us answer our question. So first, let's practice writing our expression. So since we're doing QP, we have the partial pressure of our products, which is CH4 and H2O. And then in the denominator, we have our reactants, so the partial pressure of CO and the partial pressure of H2 raised to the third power. Now plugging in those values, I have 0.4 times water, which is again 0.4, so we're just going to square that. Then I have CO, which is 0.02 times 1 to the third power. And then we're going to go ahead and solve for that. That's going to give us a QP of 8. So with this information here in the table, we know that we get a reaction quotient of A. And we know at equilibrium, we're going to be at 66, which means we are shifting towards the right or towards the products. So looking at these answer choices, that means we can automatically cancel out option B and option D because it said more H2 was produced. Well, that is false because we're moving to the right, which means we're increasing the amount of CH4 and H2O, and we're decreasing the amount of CO and H2. So now let's look at our options of A and C. So A says more CH4 was produced because the rate of the forward reaction was higher than the rate of the reverse reaction, which is a true statement. So let's just make sure C is proven incorrect. So C says more CH4 was produced because the total pressure of H2 and CO combined was higher than that of the products. Thus, the reaction shifted to the side with the fewest number of moles of gas. So this statement does have some merit when it says that the reaction shifts to the side with the fewest number of moles. If you increase pressure of an equilibrium, it will shift and do that, but that is not what's happening here. Here we have a set of values of the partial pressures of this system, and we're just trying to find out what those pressures are going to do when they reach equilibrium. So the correct answer choice will be A. So now moving on to the 3 top missed questions on the 7.3 to 7.4 AP Classroom assignment. This one says equimolar amounts of H2 and I2 are pumped into a 1 liter container to reach equilibrium. If 0.6 moles of HI is present at equilibrium, how many moles of H2 were initially added to the container? So because the reaction starts with equimolar amounts of H2 and I2, the amount of reactant that is consumed is directly related to the amount of product that's formed, because we have 2 moles of reactant to 2 moles of product. So since the problem states that 0.6 moles of HI is present at equilibrium, that means we consumed or used 0.3 moles of H2 and 0.3 moles of I2. And so if we were to solve for how much is at the start, we know that that value is going to be X minus what we know was consumed of H2, which was 0.3 moles. So using that information, I can go ahead and plug it into my equilibrium expression. So we know K is equal to the concentration of our products. In this case, that is HI, raised to the power of the coefficient, which is 2. And then the bottom is our reactants. So we have H2 and we have I2. Now, because H2 and I2 are equimolar, we can kind of treat them as the same and then just raise that value to the power of 2 because, again, they're the same. So we have K. So K is equal to 100. We have the concentration of HI, which is 0.6, and that's squared. And then we also have this value here that we came up with, which represents the amount we started with minus the amount we know was consumed. So since that value is for both H2 and I2, I can put that in parentheses, X minus 0.3 and square it, because I'm using that for both H2 and I2. So now I can use my calculator and solve for X. And that is going to give us a value of 0.360 moles, which is our answer, C. Then we have the particle diagram shown represents a mixture of NO2 and N2O4 at equilibrium. Which of the following is the value of Kp for the reaction? Assume that each particle represents a partial pressure of 1 atmosphere for that substance. So let's start off with our equilibrium expression. So we know we're doing Kp. We have products, which is the partial pressure of N2O4, divided by reactants, which is the partial pressure of NO2 squared because we have a coefficient of 2. So now let's plug in our amounts in ATM for each of those substances. So let's start off with my product, N2O4. I have 1, 2, 3, 4, 5, 6. So 6 is going to go on top. And for my reactant, I have 1, 2, 3. So it's going to be 3 squared on the bottom. When I do that, I end up getting 0.67. And that is my answer for this question. All right, so go ahead and pause this one and read this question before I move on and start talking about it. Okay, so for this question, we can see that our initial pressures, we had equal amounts of pressure for our reactants, and we can see our reactants are also 1-to-1 mole ratios. So if I am decreasing SO2 by 0.8, I'm also going to decrease Cl2 by 0.8. So my value or partial pressure for Cl2 at equilibrium is also going to be 0.20. So now that I have that information, I know option A is out and option D is out. I can go ahead and plug these values in to Kp and solve for them. And plugging in those values into Kp gives me a value of 20, which means C would be our answer for this question.